The Pew Research Center claims that 91% of all adult Americans own a cell phone of some kind. Garrett wants to see if this is true. He randomly surveys 353 adults and finds that 312 of them own cell phones. Do you think Garrett should reject the Pew Research Center's claim? Why or why not? So this is kind of an introduction to hypothesis testing. It is not yet a full hypothesis test, but it helps you understand some of the mechanics and some of the thought processes that are involved. So the very first thing that we need to identify is step one, state the hypothesis. What is the claim that we are testing? Okay, and it's in the very first sentence. The Pew Research Center claims that 91% of all adult Americans own a cell phone of some kind. That's the claim. Garrett wants to test if this is true. So we're testing if that claim in the first sentence here is true. Okay, so very first thing we have to identify is this a claim about the population proportion, or is it a claim about the population mean? Well, 91%, a percentage is a kind of proportion. So it is a claim about the population proportion. The proportion of all adult Americans that own a cell phone is 91%, according to the Pew Research Center. So P is equal to, and then I'm going to write 91%, but I'm going to write it as a decimal. So 0.91. Step two, we're going to determine the features of the distribution of point estimates using the central limit theorem. And we're going to do this, by the way, assuming that the hypothesis is true. That's what a hypothesis test is. We assume that hypothesis is true, and then we determine how likely or unlikely it is that we obtain the sample that we do. Okay? So by the central limit theorem, we know the point estimates are either normally distributed or t-distributed. Well, since we're testing the population proportion, we're going to use a sample proportion to test our claim. And we know that sample proportions are normally distributed, right? Sample proportions are always normally distributed. In fact, if you recall, the central limit theorem states that our sample proportions, our distribution of sample proportions, are normally distributed with mean mu sub p prime and standard deviation sigma sub p prime, where mu sub p prime is the population proportion and sigma sub p prime is the square root of the population proportion, p times 1 minus p over n, where n is the sample size. Okay, so now that we know it's normally distributed, we want to find the distribution mean and the distribution standard deviation according to the central limit theorem. Well, the distribution mean is the population proportion. And remember, we are assuming for now that this hypothesis is true, which means our population proportion and our distribution mean is 0.91 or 91%. And then the distribution standard deviation, to find that, we're going to need a notebook, right? We're going to use this formula here, and we're going to throw it into a notebook. So in this case, our population proportion P is 0.91. And then we will need our sample size. In this case, Garrett randomly surveys 353 adults, so our sample size is 353. And so our sigma sub p prime is going to be the square root of p times 1 minus p divided by n. All right? And here, I'm just using the formula according to the central limit theorem for that standard deviation of sample proportions. Okay, so let's type that out one more time so we get it printed out to the screen. It'll take a moment to connect, and there we go. So that is our standard deviation of sample proportion. So I'm going to copy that. I'm going to put it into the appropriate box here. Okay, so step 2 is done. I know how this is distributed. What that means is, in this case, my distribution of sample proportions is normally distributed with mean 0.91 and standard deviation, and it's about 0.0152. Okay, that's going to be important when calculating the probability. Okay, so assuming the claim is true, find the probability of obtaining the point estimate. Okay, so since we are talking about population proportion, we want to know the likelihood that we get the sample proportion that we did, or at least something at least as extreme as that sample proportion. Okay, and now comes the inequality. For this, we actually need to know what our sample proportion is. That will go here. So in this case, our sample proportion, we know we surveyed 353 adults and 312 of them own cell phones. Okay, so if you remember, our sample proportion is x over n, where x is the number of members of the sample with that certain characteristic. So in this case, 312 of them own cell phones, so that's the characteristic we're looking for, divided by the total number of members of the sample. And that was 353 adults who were sampled. So I'm going to throw that into my notebook, and that's going to give me my sample proportion. So that was, what was it? It was 312 over 353. 312 adults with a cell phone out of 353 total survey. And I'll type it out one more time so that it prints out so I can see the result. So it's 0.8838. I'll just copy the whole thing. Okay. So that is my sample proportion, and I want to know what's more extreme than that. So to understand the symbol that comes next, and let me show you your options first. It's either less than or equal to or greater than or equal to. Okay? So to understand what symbol comes next, we have to understand the kind of distribution we're assuming here. Okay? Remember, according to the central limit theorem, the mean is 0.91. So the mean of all sample proportions is 0.91. And we just found our particular sample proportion is 0.8839 about. So I'll just round that off to 0.88 for this diagram. That's smaller than 0.91. Okay? If yours was bigger, obviously you'd write it over here. Now, we want to take the probability that we are more extreme, or at least as extreme as 0.88. Have a sample proportion at least as extreme as 0.88. If we did it over here, that wouldn't include just values more extreme, right? Because all these values in the middle, they're quite common. They're close to that average of 0.91. So they are not more extreme. So we want to go in the direction of whatever tail our sample proportion is closer to. So in this case, we want the area to the left of 0.88 in the lower tail, because those are the more extreme values than 0.88. Those are the values further from that supposed mean of 0.91. Okay, so in this case, that means if I want to go to the left, that would be less than or equal to, right? Okay, and now we see another one here. Let's see what's going on here. Oh, see now, this probability, we're going to set it equal to a probability, but now we're going to have to convert it either to a normal distribution, a standard normal distribution, or a t-distribution. So in this case, we already said that our data is normally distributed. And so we would want to convert to a standard normal distribution, right? It's going to have the same inequality. And we just want to take this number and find the z-score for it. Okay, so if you remember the z-score, find a z-score by taking your point estimate. In this case, that would be p prime, subtracting the mean of your distribution, that's mu sub p prime, divided by the standard deviation of your distribution, sigma sub p prime in this case. Okay, and remember mu sub p prime, that's just your population proportion p, which we are assuming is 0.91. So let's throw that into our notebook. So we're going to find a z-score, and we want p prime minus mu sub p prime, which we said is our population proportion p, divided by the standard deviation of the distribution, which is sigma sub p prime. And this is one of the great things about using variables, is that I don't have to remember what my sigma p prime is. I just have to put in the variable there, and the computer remembers for me. Okay, so that's going to give me my z-score. So I'm going to type it one more time, so we'll print out, run it, and that's my z-score. Let's copy that, paste it in. Okay, so what this is saying is the probability that our sample proportion is more extreme than the sample proportion we actually got. The probability that we get a sample with a sample proportion more extreme than the sample proportion we actually got is the same as the probability of a z value being smaller than negative 1.7166 in a standard normal distribution. Okay, and now that we've converted this to something that uses the standard normal distribution, we can find the probability using a p-norm function. So my probability, p-norm, I'm going to plug in the z-value that I just found, and I just have to decide if I'm going to be lower tail true or false. Since it's less than or equal to, that means I am using the lower tail, right? And we could also check our picture. Right here, the lower tail is shaded. And so I'm going to set lower tail equal to true. Right? There's our probability. Okay, that's about 4.3%. Now, step 4 is not a step that's actually graded, but you should take a moment to think about this. So what do you think, based on the probability you calculated in step 3 of obtaining the point estimate, would you reject the claim? So think about this yourself. So this is the probability that we select a sample that is at least as extreme as the sample we actually got, assuming that this hypothesis is actually true. Okay, so what do you think? This is about a 4% chance that we would get this result. Now that's pretty low. That's pretty low. A lot of people would look at that and say, well, either you're really lucky, because that's a fairly unlikely outcome. Okay, and it's not crazy unlikely, but it's fairly unlikely. So either you're really lucky, or our assumption at the beginning that the population proportion is 91%, that's actually not true. Maybe it's actually lower. Maybe the Pew Research Center is wrong. So at this point, we're just kind of guessing. We're looking at this and saying, that's really low. I think the Pew Research Center is wrong, that the true population proportion is not 91%. Okay? Later on, we're going to look at this and we're going to be able to be more careful about our decision. We're going to decide in advance how comfortable we are, how unlikely our sample needs to be before we reject the hypothesis we began with. So let's submit that. And there we have it.